All right, ladies and gentlemen, 2 o'clock. Welcome back to your favorite class. Hopefully you haven't had a very happy Taco Tuesday. Hopefully you got some tacos on Cinco de Mayo. But now back to reality. I've left the screen up here just for a hot second to remind everybody that the simulation number 3 has been posted. It's on Linkages, and you could probably make your way through a good majority of it, especially after today, because today's agenda is just doing an example problem with linkages, which you will discover is long and annoying when doing it by hand. That this simulation will be due next Friday. Do we have something in the chat? Oh, no, it's just that I recorded the meeting. All right. What's the issue with the meme today? I feel like I'm finding like defective memes. So we found a square root. What's the problem? Will we be able to do the sim by this weekend? Yes, of course. We should be able to do it after today. What's the meme issue? It's a rectangle. Yeah. Oh man, it takes a bunch of engineers to tell me that that's a rectangle, not a square. Yeah. So found a square root. No, it's a rectangular root. What the heck? All right. Oh, that was funny. Not only that they're trying to be ironic with the square root, but it's not a square. It's a rectangle. Oh, terrible. Okay. So all we're going to do today is look at position and velocity analysis of a linkage using the techniques that we've been talking about over the last couple of days. All right. So I'm just going to dive right into it. I'll get up here for you guys what is the example problem that we're going to do today. All right. So here's this example problem. I'll give you guys a second to copy it down, but more or less we're going to be looking at 4-bar linkage and starting with position analysis, going through the velocity analysis to determine various things. All right. So we've got the link lengths A, B, C, and D. We've got a driving link, which is at 40 degrees. And we're told that the first link in the chain here is being driven at 25 radians per second. So that is omega 2. And then we're asked to determine the possible values of theta 3 and theta 4, which could occur in both the open and the crossed configurations. Then we want to determine the angular velocities of links B, that's R3, and C, which is like R4. And then we want to determine the linear velocity of A and B. And we'll determine those linear velocities for both the open and the cross configurations. Then we're going to sketch what this actually looks like. So a lot to do for this problem. And you will see by the end of today why it's better to do this computationally, because to do all of these analyses by hand would be horrible. So by the end of today, you'll be begging me to put it into MATLAB. You're going to say, oh my gosh, we got to write a MATLAB function to do this instead of doing this by hand. Well, that's what you're going to do for simulation number 3. So you'll be begging me, rawr, I want to do this in MATLAB. All right, so give you a second to copy it down. And then we'll get thee to the white pad, and so all we're really doing today is just doing this velocity analysis. All right. Using all the equations that we've derived and talked about. All right, so we'll get you over to the pad here. Copied everything down. Hopefully you've had time to do the same. Okie doke. And here we are. So we've got this model of our linkage that's going on here. Remember, we have link lengths A, B, C, and this fourth kind of like imaginary link, which exists between the 2 pinned points, which is like the link length D for position vector R1. So those 4 values are given to us in the problem. I'm going to assume we know what the link lengths are. And then we're told something about the driving angle. Theta 2 is 40 degrees, so that is this initial angle of what is R2. And we're also told something about the angular velocity of this first link, which is omega 2 is 25 radians per second. So here in this particular figure, this is omega 2. It's the angular velocity of this first link, which is the driving link of the system. So if that's the information that we have available to us, we want to do the position analysis to find these angles theta 3 and theta 4. Okay, and they could exist in both the open configuration, which you see here, or potentially a crossed configuration, which might look something like this. Okay, remember we also have a crossed configuration. So we're going to find those angles that are possible for both the open and the cross configuration. Then we'll find the angular velocities for both omega 3 and omega 4 for both the open and cross configurations. And then we'll look at the velocities of points A and B in both the open and cross configurations. So a lot to do here. So let's just dive right into it. First thing we want to do is the position analysis. So that's going to give us what will be theta 3 and theta 4. So if we want theta 3 and we want theta 4, we're going to need to go to the equations that look something like theta 3, 1, 2 is 2 times inverse tangent of all this stuff here, which is opposite of, sorry for theta 3, it's opposite of E plus or minus square root of E squared minus 4 df all over 2d. And similar for theta 4, 1, and 2. All right. So these are the equations that we're generally going to be using. So we need to define what are these constants like E, D, F, so on and so forth. And if you remember back, those E, D, F, and what is capital A, B, and C are dependent on these non-dimensional quantities of K. Right? So I'll say we need A, B, C, D, E, and F, which use non-dimensional quantities K1 to K5. So this is going way back to Tuesday's lecture where we defined all of this general stuff. All right, so let's start with our non-dimensional quantities, which are K1 through K5. Like I said, at the end of this, you will be begging me to go into MATLAB. Begging! Rawr! All right, go back. K1 is D on A, which is, again, just the link lengths here, D and A. This is 100 millimeters on 40 millimeters, both given in the problem, so this is 2.5. All right, K2. This is D on C, which is 100. I'm going to cut out the millimeters on C, which is 80. And this here is 1.25. K3. This is kind of the complicated one. A squared minus B squared plus C squared plus D squared, all on 2AC. All right, so we plug in here. Value of A is 40 squared minus B is 120 squared plus 80 squared plus 100 squared, all on 2 times A, which is 40, times C, which is 80. This will all get us a K3 value of 0.562. A little messy. Let's clean that up a little bit. 0.562. So again, these are all just kind of like using the link lengths, and they're non-dimensional, right? Since we're doing something like millimeters divided by millimeters or millimeters squared divided by millimeters squared. All right, continuing. K4. This is just D on little b, all right, which is 100 on 120. Which in decimal form, 0.833. All right, continuing. K5 is another kind of strange, weird one, which is going to be C squared
minus d squared minus a squared minus b squared all over 2 times a times b. All right. So here, you can punch the numbers in for yourself. I'll cut out that little bit of information, but we get negative 2.04 for K5. All right, so creating for ourselves these non-dimensional values of K, which will feed into the variables capital A, capital B, capital C, all the way to capital F. All right. So these are our general values that we'll be using in the upcoming expressions to get capital A through capital F. All right. So now I need capital A through capital F. All right. Capital A, we recall, is cosine theta 2 minus K1 minus K2 cosine theta 2 plus K3. All right. So here this will be cosine 40 minus K1, which is 2.5, minus K2 cosine theta 2, which is 1.25 cosine 40 degrees, plus K3, which is 0.562. So we get a value of A, which is negative 2.13. All right, B. B is a little bit easier, and B is the same as capital E, so capital B and capital E are the same. And this is negative 2 sine theta 2. It's negative 2 times sine of 40 degrees, or for us here, this is negative 1.29. All right, and this is also the same as capital E. All right, making our way. Capital C. Continuing with our equations, K1 minus K2 plus 1 times cosine theta 2 plus K3. We can plug this in. We have all these values. We'll get the value of C going to be equal to 1.34. So recall our capital letter D. Cosine theta 2 minus K1 plus K4 cosine theta 2 plus K5. All right, we got all these values. So we can solve directly for capital D, negative 3.14. Ironic that it is negative pi. There's no actual reason why that should be. It just kind of works out to that particular value. All right, well, all right, negative pi, rawr. F, haha. You guys are all familiar with that, right? Capital F. Seen that once or twice. Just kidding, just kidding. You're all getting good grades. You're all getting capital A's. Actually, you're getting capital P's for pass this quarter, so. K4 minus 1 times cosine theta 2 plus K5. All these guys you have, again, capital F is 0.331. All right, who's annoyed yet? Anybody annoyed by all this algebra? Yeah, annoying. That's kind of the purpose of today. So buckle up and be annoyed. We got all these non-dimensional values that we have to solve for. Here, more non-dimensional values for A, B, C, D, E, and F. And finally, after doing all of this algebra, plugging all of this stuff in, now we can get around to solving for our values of theta 3 and theta 4. All right, so just a reminder what those equations are. For whatever reason, they use theta 4 with capital A through C, and they use theta 3 with capital D through E. So we'll start with theta 4. And remember, we get two solutions here. And the general equation is 2 times the inverse tangent of here for theta 4. It's negative b plus or minus the square root of b squared minus 4 capital A capital C all over 2 capital A. So we'll work this. 2 tangent inverse of, we have all of these things. B is negative 1.29. We go back up here, negative 1.29. So with the negative sign in front, it's going to turn to positive. So here we have 1.29 plus or minus the square root of negative 1.29 squared minus 4 times capital A, which is negative 2.13, times C, which is 1.34. And this is our general expression here. All over 2 times A. So this is 2 times A, which is negative 2.13. So here's your expression for theta 4. Let's take a look at this quadratic really quickly, just so we're on board. This guy here, when we square the negative, is going to be positive, and then we're going to subtract from it this negative value. So we'll add to it a positive value. So this term here will be positive. After we subtract the negative, then generally the contribution from this will also be positive. So we'll end up with a positive value under the square root, meaning that we will have real solutions, not imaginary solutions. Okay, so we're checking to see if our solutions are imaginary, and they would only be imaginary if those values of underneath that particular square root, or the rectangular root, as we have discussed previously, were negative. So we've seen here now, after doing the algebra, that in this particular case, we should have a positive value under the square root, resulting in 2 possible answers for theta 4. All right. So if you work through this with the plus and the minus, you'll get something like theta 4, 1, and 2 are equal to negative 98 degrees and 57.3 degrees. All right, so these are the 2 values that you should obtain. Not quite clear exactly which one is going to be the open configuration, which one's going to be the cross configuration, but I've looked ahead and I'll generally tell you that this will be the crossed and this guy will be open. You can sort of see why that would be. Remember, the angle of theta 4 is associated with the length that's kind of on the far right-hand side. So negative 98 degrees would probably indicate a cross configuration. 57.3 degrees would probably indicate an open configuration. So what I mean by that is, if we go back up to our model here, here's our value of theta 4. If it's negative 98 degrees, that means it's down to roughly about here. So that link is in like this configuration for negative 98 degrees. All right. So it's probably likely that this is going to be like some crossed configuration. All right. Now, opposing that is the 57.3 degree entry, which maybe looks something like this. So here's your 57.3 degrees, which would indicate that this is probably going to be the open configuration when you consider something like this guy connecting. All right, it's going to look like an open configuration. All right, so you can see that the 57.3 sort of intuitively is probably going to be the open configuration, and the negative 98 degrees is going to probably be the cross configuration. So hopefully we're kind of understanding what that is physically after going through the math. All right, so similar for theta 3 with 2 solutions, and that we're going to have theta 3, 1, and 2 is 2 times the inverse tangent of this general equation, which looks something like opposite of E plus or minus the square root of E squared minus 4 capital D capital F all over 2 times, well, where did my 2 go? Oh, there, it came back, weird. 2 times capital D. All right, so put in values. And you'll find that because we have real solutions for theta 4, we would expect real solutions for theta 3, which is what we observe here. And you'll find that theta 3, 1, and 2 are equal to the following. It is negative 61 degrees and 20 degrees. More specifically, 20.3 degrees. Again, not necessarily obvious which one of these angles goes with open and crossed immediately, but I've looked ahead. Here's your crossed, and here is your open. Again, this sort of makes sense for theta 3, negative 61 degrees and 20 degrees. So remember that our initial angle of theta 2, which is this first angle here, is 40 degrees. So what you see in this picture is approximately right. I mean, it might be a little shallower than that. So we can imagine that our first link probably looks something like, I don't know, something like this. And then our second link is either got this angle of what we just saw for negative 61 or positive 20. So if it's positive 20, it's probably going to be coming up something like this. All right, so here is like the 20-degree angle. And this is going to correspond to this open configuration where, remember, this was something like 57 degrees. All right. So that's kind of like what your open configuration is probably going to look like. And if we consider now the alternate angle for this theta 3 from our configuration, that alternate angle here is the negative 61 degrees. So if we consider a negative 61 degrees for this guy, that's going to be roughly here, right? A pretty steep, negative 61 is like roughly here. So from the horizontal, here is a negative 61 degrees. So here's like where the second link would be in this sort of chain. And that's going to like correspond to when we had that like negative 98 degree angle over here. All right, so this is approximately what our rig is going to look like, and you can see that this is clearly like a crossed configuration. All right, so hopefully it might take a little bit of intuition to understand which angle goes with open, which angle goes with crossed, but if you just like think about it a little bit, it comes pretty clear and pretty apparent. All right, so let's call the crossed configurations like the theta sub 1, and let's call the open configurations like the theta sub 2. All right, it's just since that's how I've kind of written them. All right. So here we'll go back up here and we'll say the crossed value of negative 98 degrees is like theta 4, 1. Here this open is like theta 4, 2. Same thing down here. Crossed is theta 3, 1, and open is theta 3, 2. Right. So that's what we'll assign going forward as we move to the velocity analysis. So at this point, the position analysis is done. Right. Yeah. All right. Give yourself a high five. Self five. Yes. All right. A lot of algebra, annoying. Would be easier in MATLAB. We all agree. Well, there's your position analysis. Now onwards, velocity analysis. All right. So remember, we have all the link lengths. We have the angular velocity of the first link, which is omega 2. And now we have all these angles, theta 2, theta 3, and theta 4 for both the open and the cross configuration. So with that, we just plug into our general velocity equations to get like angular velocity and linear velocities. So I'll remind you what those equations look like. And so for angular velocities, we have something like omega 3 is a omega 2 on b times sine of theta 4 minus theta 2 divided by sine of theta 3 minus theta 4. And for omega 4, we have a omega 2 now on c times, here this is the sine of theta 2 minus theta 3 all over sine theta 4 minus theta 3. All right, so those are your general equations. We sort of talked about how those were derived over the last couple of days. So here are angular velocity equations that we're going to use. And remember that we're going to get two angular velocities, one for the open configuration and one for the cross configuration. Okay. So let's go ahead and look at this separately. Let's start with the cross configuration. And here, remember, we're using like theta 3, 1 and theta 4, 1, which were theta 3, 1 here for us was negative 61 degrees. And theta 4, 1, I have to remind myself, was negative 98 degrees. Negative body temperature. Okay, baby, let's go. So those are the angles that we're going to use here. And we'll remind ourselves that the problem gave us omega 2, which was 25 radians per second. All right, so with that information, we have all of the stuff that would feed into omega 3 and omega 4. So we just got to do it. So here, general expression, omega 3. And let's call this omega 3, 1. Since this is in the cross configuration, we're using the subscript 1. So omega 3, 1 here is A omega 2 over B times the sine of theta 4, 1 minus theta 2 divided by sine theta 3, 1 minus theta 4, 1. All right, we have all of these values. You can just plug it in. You're going to get a unit here or an answer here that has the same units as this omega 2 because everything else kind of cancels out dimensionally. And you'll end up here with an omega 3, 1 of negative 9.3 radians per second. All right. Similar idea for omega 4. Here we have A omega 2 on C multiplied by sine theta 2 minus theta 3, 1 over sine of theta 4, 1 minus theta 3, 1. Punch the numbers here, you'll get negative 20.4 radians per second. All right, so these are the values of the angular velocity of the links in the crossed configuration. All right, now the open configuration. Same idea. Here omega 3 is equal to A omega 2 on B times, a little bit different here now, so we have sine theta 4, 1 minus theta 2 all over what is sine of theta 3, 1. Oh, not 1. We're doing the open configuration now, so we need theta 4, 2. Sorry about that. Sine theta 3, 2 minus theta 4, 2. Right. Similar idea, except we've now just used the coordinated angles theta 3, 2 and theta 4, 2. Plug in here, negative 4.12 radians per second. And then our angular velocity of link number 4 in the open configuration, so we'll use the subscript 2 here, is going to be A omega 2 on C times sine of theta 2 minus theta 3, 2. All on sine of theta 4, 2 minus theta 3, 2. All right, looks like I might have a question here. Sorry if that question's kind of been sitting. stewing for a bit. What would happen if theta 3 and 4 values were imagination? Okay, thank you for the question, Peter. If they were imagination, that would tell you that the linkage could not be configured with the links given. All right, that could be possible if there are many configurations where that might be impossible. So if you're given a very long length of the spacing between the two pins, so here, let's say the spacing between these two pins is very big, right? So let's say this is like 1 billion. 1 billion between these two guys, and then all the rest of these links were really short. All right, there's no way that you could assemble the links with enough freedom to get all the way out to whatever separation you have between those two guys. So if the value of little d there was like a very large number relative to the size of the other links, then you would get an imaginary solution for theta 3 and theta 4. So we kind of talked about that a couple days ago. All right, back to reality. Oops, there goes gravity. So here we're looking at the angular velocity of link number 4 in the open configuration. Here we're going to get 7.0 radians per second. Hopefully you're starting to see why the computational assignment is going to be useful here. All right, let's say you're looking at certain configuration of linkages, and then you're like, oh, what happens if I just like extend this link just a little bit? You want to go through all that algebra? I don't. Like, you just change one little link length, and now you got to do a bazillion lines of algebra again. Yikes. They used to have these jobs, like back in the 50s, called calculators. All right, that was literally the name of a job, where people would sit at a desk and do calculation all day long. Okay, they sit at a desk and you're like, all right, what happens if the link length is this? What happens if the link length is this? And people would just like go through pages and pages and pages to figure out the answers. Okay, this is before computers, or before computers were useful. So, you know, they had to do this crap by hand 50 years ago. I guess it's 70 years ago, but you get the general idea. It's that, God damn, this would be horrible if you had to just do this by hand all day long. I would hate that job. Right, but that job existed, so good job, technology, for bringing us into a place where we don't have to do that, where we can just click a button in MATLAB, and we get the answer. All right. So there are your angular velocities. Let's make a sketch of our piece before we go any further, because I think that will be helpful. All right, so here's our sketch, and we're going to sketch this guy in like the what would be like the XY plane or the real imaginary plane, however you want to think about it. And I'll do my best to try to like keep this to scale. All right, so we're told that we have, I'll just remind you what the lengths are here. A is equal to 40, B is equal to 120, C is equal to 80, and D is equal to 100. All right. The angle theta 2 here is going to be equal to 40 degrees. And then theta 3 is, depending on open or cross configuration, we have what would be negative 61 degrees or 20.3 degrees. And then we have a theta 4 that is either negative 98 degrees or 57.3 degrees. Right. And remember that this is like crossed and this is open configuration. Right. So let's set our baseline. This angle D, or this length D, is the distance between the pins. So we know we have a pin over here and we got a pin over here. So that length here, if we're measuring this out, is a length of 100 millimeters from that left-hand side. Okay, so this guy here is 100 millimeters. Great, fantastic, marvelous. Now we have coming off at a 40-degree angle here. So let's try to do our best with like a 40-degree angle. The link that is link A. All right, so that's about 40 millimeters long. So we'll try to scale it with that 100. So if it were laying flat, it might be about right there. So I'm going to try to draw that approximate length, but at that angle of 40 degrees. So that might put me out about like right, somewhere about like right here. All right. So out here is typically what we would call like point A. So this angle here, 40 degrees. And on our way is our sketch. And remember, this length here is also a length of 40 millimeters. So we can include that in our sketch as well. Now is where we sort of diverge and look at our open and cross configurations. So let's start with, let's start with the cross configuration first. Why not? So the cross configuration, we have the angle theta 3 here now is negative 61 degrees. So I'm going to create for myself a horizontal here. And negative 61 degrees from that horizontal, I will be applying the link B, which is 120 millimeters. All right. So I need an angle that's negative 61 degrees. So maybe that's, I don't know, roughly about like here or so. It's negative 61 degrees. And this is going to extend a distance of 120 millimeters. So I got to go down there pretty far. All right, so about the length from the left-hand side to there is maybe 120. So I need about this length of a link to get me down there. So it's going to have to extend pretty far down at this like negative 61 degree angle. All right, I think maybe that's appropriate, getting pretty close there. All right, and down here now, we have what is our point B for the cross configuration. So B cross configuration. All right. Last thing I might want to do is look at the link C, which is coming off of this point over here. And it's coming off at the angle of theta 4 for the cross configuration, which is negative 98 degrees. Right. So coming off here at negative 98 degrees, maybe that looks something like this. And here is theta 4, which is negative 98 degrees. And this, if I did things correctly, should line up with point B. So not quite exactly right, but pretty close. All right. So this angle here is the angle theta 3, 1, which is negative 61 degrees. So here is your crossed configuration. All right, giving you some information there. Now let's look at our open configuration, which I'll do in blue. So the open configuration is going to use the same lengths, it just has different angles. So here we've got an angle of theta 3 is 20.3, and an angle of theta 4 is 57.3 degrees. Right. So again, we have our same horizontal. Now I'm going to look at the 20.3 degrees, and so that might be coming off here at an angle that looks something like this. This is about a 20-degree angle or so. And again, this link is relatively long. So again, it's about 120 millimeters in length, so I really need to blast this guy out here. All right, he's pretty far out there. Pretty far out there, just like my personality. All right. And here we have point B in the open configuration. All right. So finally, completing the circuit here, we've got the final link that's kind of coming out from this particular point. It's of length C, which is 80 millimeters, and it's coming off at an angle of theta 4, which is 57.3 degrees. Okay. So here our final link in the chain of our open configurations here, where this angle is 57.3 degrees. All right, so there we go. This guy is 120, this guy is 80, this guy is 120, and this guy is 80. So there you go. Crossed in your open configurations. Sketching from generally the position analysis. Now, I want to talk now about the angular velocities of each one of these guys as well. So this link, first link in the chain here, is like driven by the angular velocity omega 2. So in this particular situation, we know that this link is being driven by omega 2 equals 25 radians per second. So let's take a look at what we solved for the angular velocities of like the second links and the third links in the chain in both the open and cross configurations. So let's bring that information in here as well. Let's first look at the cross configuration. All right. So here we have this cross configuration where you've got something like omega 3 is equal to negative 9.3 radians per second. So what that means is at this particular point in time, the crossed configuration, this particular link here is moving with an angular velocity of negative 9.3 radians per second. So this guy is kind of rotating in this general direction, negative 9.3 radians per second. So that's kind of an interesting find there, is that this first link is sort of driving things, and that guy's kind of coming down with that particular direction. That sort of makes sense if you think about it physically, right? The other link that we saw is omega-4 for the cross configuration, which is like negative 20.4 radians per second. So this guy's really booking it in the negative direction here with an angular velocity of negative 20.4 radians per second. All right, that guy's really like coming across pretty hard there. So that sort of physically kind of makes sense with the way that those linkages are configured. I can get behind that. All right, now let's look at the open configuration. The open configuration, you have, again, like a omega-3 and an omega-4. Don't forget your omega-3s, dang it. Omega-3 has a generally small negative value, and omega-4 generally has a small positive value. So omega-3, we're going to have a generally small negative value, which is negative 4.12. So this guy's got an angular velocity in this direction of negative 4.12 radians per second. All right. Maybe I could believe that that is happening. Okay. And then the other link is omega-4, which is positive 7. So this guy is rotating around this general direction with 7 radians per second. So this is kind of the sketch of what's going on with this particular linkage. Now, there's a lot going on here, but hopefully we can sort of understand and see what's going on. Does this make sense physically? Yeah, I think I could buy that. Right? Like this guy, this particular link is like coming down and like folding in. So this particular pin at A is kind of like really trying to push down in this general direction for the open configuration. Yeah, I could buy that. I could get behind that. So this is kind of a good sketch, a good thing to sort of check your work and make sure that you have some sanity. All right. I've lost all my sanity because I've been inside for 50 freaking days in a row, but you know, we're all losing our sanity. So it just happens faster for others. Okay. We're not quite done. We still need our velocity analysis. Just like the velocity of A and the velocity of B. So we've still got these pins here that is like the velocity of A, and what's going on with the velocity of B in the crossed configuration, and what's going on with B, the velocity of that point in the open configuration. All right. So pretty easy to see that the velocity of A in both configurations is the same. All right. And our general equation here is just kind of going to look like omega cross R. All right. But if we do it in complex notation, the velocity at A is something like A omega 2 times what is negative sine theta 2 plus J cosine theta 2. Here for us, A is a value of 40 millimeters. Omega 2, given in the problem, 25 radians per second. Multiplied by, here now I have this complex direction. So this is negative sine 40 degrees plus J cosine 40 degrees. All right. If I work through this, I'll have real and imaginary components that look something like negative 643 plus 766 J radians per second. That's your velocity of A at this particular instant. I have a question. Another question. Solving linkage problems by hand, ain't nobody got time for that. A meme made on the fly. I like this. After the position analysis, should we try and visualize which angles belong to cross and open in order to label 1 and 2? Yes, that's a very good idea, Jorge. Thank you. The in-class meme created during lecture. Wow. Katie, good job. All right, so remember that this is like your X direction, and this is like your Y direction. All right, So let's go up to our figure and look if this sort of makes sense. Negative 643x 766j. So if this particular link has angular velocity 25 radians per second in this general direction, then we would expect the velocity vector coming off here v at a to look something like this, since it's perpendicular. So positive in the y and negative in the x. All right, which is exactly what we see with this particular analysis. Positive in the y, negative in the x, or positive in the imaginary direction, negative in the real direction. All right, so I like that. I like how that particular velocity vector at A looks. Let's finish it off. Remind ourselves that the velocity vector at B, the general equation, looks something like c times omega 4 multiplied by negative sine theta 4 plus j cosine theta 4. And in this situation, if we want the open configuration, we'll use theta 4 2 throughout and omega 4 2 for open. And if we want the cross configuration, then we'll use the ones. I guess I should have done it the other way, since I drew them the other way, but you get the general point, is that you pick the one that you want, and then the velocity at B associated is either 2 or 1 associated with the open or the cross configurations. Right? So fine. I believe that you guys can punch all those things in. And so here we have velocity at B, and I will write what will be in the cross configuration. So for us, we label that as 1. This is the cross configuration. Is going to be negative 1610. Come on. Negative 1610 plus 227j millimeters per second. This is a vector form. All right, magnitude and direction both included. This is cross. And then we also have the velocity of B for the open configuration, which we labeled as 2, is going to be, if we work through this, negative 471 plus 302j millimeters per second, and this is for the open configuration. All right, so let's look at each of these. Velocity of B, situation 2 for the open configuration. I have a negative x component and a positive y component. So let's go back up to our figure and take a look at this. So we have velocity of B in the open configuration. So here we are with our open configuration. I'm looking at the velocity of B in the open configuration, which is the velocity of that particular point there, that particular pin. And I know that if I have this angular velocity that's negative 4.12, I might expect the velocity of that point relative to A to be in a certain direction. But what's a little bit more telling is what's going on here, which is the angular velocity of this link that is sort of like fixed here to this particular point, right? So here, 7 radians per second in this positive sort of direction. I would expect then that the velocity at B coming off might be perpendicular to this, so the velocity at B here might look something like there. Velocity at B. So positive in the y, negative in the x. That's what I see here for the velocity being the open configuration. Positive y, negative in the x. So that looks pretty good. And lastly, let's look at what's going on for the velocity of B in the cross configuration. Here I've got this negative 20.4 radians per second. So I would expect, since it's rotating in that general direction, a pretty strong component here in the negative x, or the negative real direction, and a slight component in positive j. And that's exactly what we have. Very strongly negative in the x and slightly positive in the y, or the imaginary direction. Okay, so there you go. Full-blown linkage. Anybody out there crying? Okay, are you crying? There's no crying in engineering. No, I'm just kidding. There's lots of crying in engineering. Are you ready to go to MATLAB now? Because that sucked. All right, I don't want to do all that algebra every single time. Yeah, I want to write it in MATLAB. So that's why I gave you the simulation for this particular portion of the class, because doing all these things by hand is annoying. All right. Hopefully you learned something today, and that you learned that linkage analysis by hand is annoying.
That's what I want you to take away today. All right, that's it for today. Thanks for coming. We'll see you tomorrow.